All right. This one's a long one, so buckle up. So a little bit of a refresher back from our honors chem days. You got kinetic energy is proportional to all temperature of objects. We've been covering that for a few units at this stage. Heat transfer occurs from collision of particles. Think of like transfer of kinetic energy in billiards, or what we might call pool. One ball hits the other, transfers its energy, it carries on, and the original speed of that billiard ball is going a lot slower than it had been. Different states of matter have different transferring capabilities due to this contact. The idea is that things like gases come into contact less than things like solids or liquids. So in thinking of something at high energy before a collision, some kind of surface that's occurring, the temperature is going to see the kinetic energy is going to be higher and then slow down. The low energy before a collision is going to be low energy and then higher afterwards. Heat conduction always goes from high to low. We see this concept of different states of matter in the thinking of a conduction through a ceramic mug. You got hot liquid as coffee, you got the ceramic mug, which is solid, and you have the gas on the outside. If you ever put your hand close to a mug but don't touch it, you can feel it be slightly warm, but not very hot, because again, those gas particles aren't staying anywhere near it. You touch the mug, ouch, hot, coffee, ouch, hot. So those points of contact are much higher in the solid and the liquid than in the gaseous form. All right, so let's take a look at thermal energy transfer. Block of metal, hot, added to water, cold. Energy transfers from the metal to the water. Makes sense? Higher temperature to lower temperature. Now, exact temperature change depends on a few things. Mass, specific heat, change in temperature of the metal is going to be equal to the mass, specific heat, and change in temperature of the water. Essentially, the metal's energy being given off is the same as the energy of the water being taken in. Now, think about what we would have for our values. Mass and specific heat are always positive values, change in temperature. This is going to be a decrease because the metal started hot, so therefore it'd be negative. The water's going to warm up, that would be positive. Negative over here, positive over here. That's why we have a negative sign added to the equation. Now, this negative sign can be on either side. It does not matter. This negative sign is just a mathematical correction. If we had the negative over here, because we have a negative delta T, this side would be positive. This would just be positive value, positive value, positive value, also equal. So the negative can be on either one. Again, the negative is a mathematical construct, not a scientific one. It's not talking about energy being released. In this case, we have water is actually endothermic. It's taking in energy. The metal is exothermic, releasing energy. So this negative sign, again, not representative of scientific principles. It is there for a mathematical correction. You'll see on a subsequent example, we'll switch the negative, put it on the other. It does not matter. And that's this one. So we've got a bar decreasing by 10 degrees. That means it must have been hotter. The water must be warming up. We're trying to determine what is the temperature increase of the water. So we plug our values in. You can see that they put the negative on the metal side. Doesn't matter. You've got the values each for the water, the values each for this. You can see the negative cancels out, leaving a positive value on the left, positive on the right. And we have our change in temperature of 1.51 degrees Celsius, solving for delta T. Another example, this one is water of different amounts. You can see that it's got colder one, hotter one. What's the final temperature after everything is mixing? Now this is a more challenging idea because you have the final temperature. The final temperature is going to be the same. Now this one being a multiple choice is trying to have you think about how do you answer this without actually doing it. We're going to go through how to do it too, but that's a lot more complicated. So if we have them being equal, and we have the ideas of what is each being said, we can take some things off if these are equal, right? We could cancel out the 4.18s. We have our masses, and we have our changes in temperature. So we can see that this one is, what do you want to call it, less than half of what we have there. won't end exactly halfway, closer to 36 than 22. Can't be higher than 36. So we know that this one's no good. So we try to think of which way this would be. Now you might say, that's a little hard to do. How would I do it in the end? And that's a little bit more complicated, but I'd be happy to show you. So let's get into it. Now, again, just a little review idea. This is for one object, but if we had two objects, they're equal to each other. Again, you can see it doesn't matter where the negative is, left side or right side. These would have equal temperatures all at the end. You get all the variables you solve for the one you're looking for. When it's mass, change in temperature, CP, those are all very simple. However, when it's final temperature, that's when it's tricky. Remember, delta T is temperature final minus temperature initial. It can be negative in the sense of something cooling. And in real terms, there's always something cooling. So again, think about what you have. I think I usually put my negative on the one that's cooling, but it doesn't really matter. So let's say we've got a block of aluminum and a titanium plate, two different metals, two different masses. The aluminum had an initial temperature. Its final temperature is 17.8. What's the original temperature of the titanium plate? And we have our specific heat values. So I like to organize my things by substance. Makes it a little easier to see and follow. And I like to try to start off with my original equation that we had on the previous, this one here, in order to solve for the temperature change or solve whatever variable I'm trying to look for. Because then I can plug it in, keep my sig fig straight, don't round so much, and be able to get a nice value. So again, it helps me keep straight of which values are which, because that's also another place where students can go wrong as they switch the masses or switch the specific heats or whatever the case may be. So I plug my values in, all of my units are canceling, and I solve for delta T. Far too many students want to try to solve for like the initial temperature by itself by, what's the term, distributing the delta T. Don't do that. It makes it a lot harder. Your delta T for the titanium is 112.6. I can now solve for my final temperature minus my initial temperature, do my math, and see that again, this will be a positive value. This will be a negative value due to the subtraction, which means when I multiply both sides by negative, this now becomes negative and this becomes positive. And I always think, does this make sense? Does this mean that this was a really cold temperature that got up to, around room temperature? Well, it's smaller in mass, has a much smaller specific heat. And so if this decreased, 60 something degrees, this coming up 60 degrees is kind of reasonable. But then I also see that its specific heat is less and mass is less. So that makes more sense that it'd have further to go than just like 60 degrees. Now remember when I said it's harder to do final temperature? Here I'll show you why. So, new block, new stuff, new stats. Now, the final temperature of the two having enough time to go through. Now, you can try plugging all the numbers in, but I'd like to show you how you can derive the temperature final into an equation that you can use. So, we've got my hot object, my cold object. I've separated out the change in temperature, so I'm having the same starting point. I need to isolate the variable TF, which is on both sides. So first you distribute, okay, watching your negatives and your positives. Next, I want to get my TFs to one side and my non-TFs to the other side. So I add this one here, add this one here. So this gets me all of my non-TF variable stuff on the left and my TFs on the right. I factor out the TF, right, by leaving that there. And then I divide both sides by what I factored out, leaving me with all of these values, again, mass, specific heat, temperature initial of, in this case, I call it the hot object, mass, specific heat, temperature initial of the cold object, divided by the mass and specific heat of the cold, plus the mass and specific heat of the hot. So essentially your energy of each divided by your, or I should say the energy you started with initially, right, because the temperature initial, divided by your mass times C of each of them. So not too hard when you really think about it. That'll get you your temperature final. Now you're going, oh my God, do I have to derive this on the test? No. Will they even ask you a temperature final? They could. This is within your capabilities. But when you have this derivation, then you're just plugging numbers in. So I'll just keep it here so you can see it. We've got all the numbers listed off from the previous problem. I literally plug it all in. You can see everything cancel out, and my temperature final is 28.3 degrees, which makes sense that this one cooled off a lot, this one warmed up a lot, this one's smaller specific heat. I'm going to expect a higher temperature jump. But again, once you have this set up, you plug it in, careful using your calculator, and you can determine any amount of temperature final. Come in with your questions, and I'll catch you on the flip side. Take care. Bye-bye.